Hello and welcome back to Introduction to General Relativity. In the previous lecture, we commenced our journey into the theory of general relativity by reviewing some of the fundamental assumptions underlying Newtonian physics. In today's lecture, I'm going to introduce to you the two main big principles that underlie the formulation of general relativity and motivated Einstein to discover the theory of general relativity in the first place. Namely, we're going to discuss the principle of equivalence and Mach's principle. So the modern formulation of general relativity is now consists of a large amount of mathematical formalism, but this formalism is very naturally a consequence of a couple of physics principles. And the first principle, and really arguably the most important principle underlying the formulation of general relativity, is what's known as the principle of equivalence, or Einstein's equivalence principle. So write that down. So the first and certainly most influential principle underlying general relativity is this Einstein's equivalence principle, EEP for short. Now, Einstein's equivalence principle consists really, in the modern understanding today, of really three parts. One of them we've already seen. So the first part we saw in the previous lecture, and that's the principle of UFF, universality of free fall. UFF, and this has another name. It's also known as the weak equivalence principle. Or WEP for short. And the content of this principle, what we discussed in the previous lecture, it says that spatial orbits of test particles only depend on the initial conditions and not on the physical or chemical properties of a test particle. UFF, WEP have been experimentally verified. E.g. in torsion balance experiments. I mean, it's a bit rush to say that they've been verified. They've been not rejected. A key point in physics, of course, is that we can't confirm a hypothesis. We can only reject a hypothesis experimentally. Okay, that we really discussed in more detail in the previous lecture on the consequences of UFF. In today's lecture, I'm going to now introduce to you the other aspects of the Einstein's equivalence principle. The second aspect is local Lorentz invariance. And this is abbreviated LLI. And it says that in a freely falling reference frame, the laws of non-gravitational physics are those of special relativity. So in particular, they don't depend on spatial orientation or velocity. So I'll just quickly summarize that. In a freely falling reference frame, the laws of physics are those of special relativity. And you can summarize this as saying that there's no preferred reference frame. And we talked about preferred reference frames in Newtonian physics. And this is one of those notions that you have to give up on when you transition to special relativity, but not general relativity. you already have to give up on it when you go to special relativity. So laws, in particular, the laws of physics don't depend on velocity or rotation or orientation. Orientation or velocity. Now, local Lorentz invariance is an assumption that a hypothesis, and you can reject the hypothesis. And Michelson-Morley type experiments have been unable to reject this hypothesis, the hypothesis of LLI. And they've delivered to us the best bounds, which are now of the order of delta C over C is something like 5 by 10 to the minus 17. So pretty extraordinary bounds on the variation of the speed of light as you change orientation or reference frame. There's a third aspect to what we now call Einstein's equivalence principle, namely local position invariance. Right? Maybe it's kind of obvious, but you got to spell these assumptions out. This is LPI, and this simply says that the laws of physics do not depend on position. So SR holds, special relativity holds, independent of space-time position, right? You know, you can have position in space, but you also have position in time. So there's another way of saying this is there's no preferred location in space-time. And you can reformulate 3 if you like to perhaps a more familiar formulation, one that Einstein, or certainly motivated Einstein heavily. And this is the principle of the universality of gravitational redshift. So principle 3 is also equivalent, which is an exercise for you, to the universality of gravitational redshift. Otherwise known as UGR. Another way of saying that is that clock rates are universally affected by the gravitational field. So this is a fundamental assumption underlying the Einstein's equivalence principle. Now, to get you into the mood and spirit and into practice with these kinds of calculations, we're going to set an exercise. This one's will be on the homework sheets, but all these exercises on the homework sheets will be mentioned in the lecture. So we're going to show you, the task is to show or argue that for small velocities and weak gravitational fields, so we don't expect any black holes or anything. So for weak gravitational fields, such as what we experience here on Earth, that delta nu over nu is equal to delta phi over c squared. So where I'm going to tell you what these symbols are. Nu x1 and nu x2, these are the clock rates of 2 clocks. We'll name the clocks as clock 1 and as clock 2. and these clocks are at locations x1 and or x2. So there's a picture, right? You have somehow a clock here, and then you have a clock here at another space-time locations. There's somehow x1, x2. So what's phi? Phi is the gravitational scalar potential, which we met in the previous lecture. So it's phi of x1, phi of x2, and delta phi is just the difference, of course, between these two scalar potentials. So gravity is pointing somehow down in this picture. So delta phi is phi of x1 minus phi of x2. And your task is to argue that delta nu over nu, the difference in these clock rates, is proportional to the difference in the gravitational scalar field divided by the speed of light squared. You can do that with a Doppler shift argument, or you can use, if you like, the quantum expression for the energy of a photon, and argue how that would change at different points in the gravitational field. There's two ways to at least to argue this relation. And the second part of this exercise is to estimate delta phi over c in our gravitational field of the Earth for a displacement of 30 centimeters. So when the two clocks are only 30 centimeters separated, which I can indicate almost by my hands here. There we go. It's about, well, a bit less, 25 there. And estimate that this change in these ticking of these two clocks. And you'll get a small number, right? And the interesting thing is, you should do a bit of Googling. What's the best bounds delivered by atomic clocks on measuring clock rates? And you should conclude that this is now routinely measurable in laboratory experiments. In fact, if you are curious, you should investigate what are the current bounds now on differences on delta, on the differences between on the differences of heights where the gravitational redshift is measurable in laboratory experiments. You'll be pretty surprised by what we can measure in the lab in terms of gravitational redshift. So it's a curious thing. So that's already, what have we done? I've described to you the principle, Einstein's equivalence principle, as it's a modern formulation of EEP, as it is found in the modern formulation of general relativity, and I've isolated three aspects to EEP, namely the universality of freefall, local Lorentz invariance, and local position invariance, or UGR, the universality of gravitational redshift. Now, it's an interesting observation that using EEP, you can derive that gravity should be described geometrically. So you've probably heard that Einstein's general theory of relativity is a geometrical theory. Sounds pretty magical, right? Pretty amazing. Lots of people have said lots of things about this. And where does this come from? Well, it's possible to derive this. You can, I would say, argue this from the EEP. And I'll give you a reference. It's not a very readable reference, I'm afraid. I took a look at it. I think you have to be, you wouldn't read this on your first encounter with general relativity, but you might be curious to see where these arguments are laid down. You can find them in this journal article here by Thorne, Lee, and Lightman. I wouldn't recommend you, as I said, if this is your first encounter with general relativity, I wouldn't really recommend following this up unless you're particularly motivated. And this is a key feature of general relativity, that it's formulated in a geometric fashion. However, there's a key point I want to emphasize, and that is that just phrasing a physical theory in geometrical terms is no particular magic. You probably heard, if you encountered any amount of popular science, the idea, statements that general relativity is special because it has this geometric formulation. Well, it's not special if a physical theory has a geometric formulation. In fact, most, if not all, physical theories can be formulated geometrically. For example, Newton's theory can be formulated geometrically, thermodynamics can be formulated geometrically, statistical mechanics and quantum mechanics may be described geometrically. In particular, quantum mechanics can be described in terms of Kähler manifolds. You can see that in my lectures on symplectic mechanics and symplectic geometry and classical mechanics. If you're willing to work hard enough, I claim you can just about formulate anything geometrically. So the important point about Einstein's theory of general relativity is that the key physical principle underlying this geometrization is that all matter, from electrons, protons, gluons to the Higgs, they all couple to the same geometry, namely that of space-time. So that's the fundamental thing that distinguishes general relativity as a geometrical theory from any other theory. And so let's write that out. That's really important. So all matter couples, doesn't matter what the matter is, right? Higgses, gluons, you name it, quarks, they all matter couples to the same geometry. We can't quantify this mathematically yet. We will be able to as we go through this course. And what geometry? Namely that of space-time. When you formulate all these other aforementioned theories geometrically, you don't see that. This is something very special about general relativity. And because of this, a single metric suffices to describe all interaction, or all couples. And I'll explain to you what is a metric later in this course. So don't worry about metrics, we will talk about them later in the course. To get you in the spirit of things, we're going to do some calculations now. These calculations are supporting various aspects of EEP with respect to Newtonian physics. And I find these calculations pretty enlightening, especially since very soon, like in the next couple of weeks, we're going to commence our studies of differential geometry, and you'll quickly get bamboozled with affine and Christoffel connections and blah, 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 and you might wonder if these actually have anything to do with physics at all. Indeed, they do, and we'll see many of those geometrical things turning up already in this quite simple calculations that we can do within Newtonian physics right now. Okay, let's take aim at the following statement. So the statement is, no external static homogeneous, these words are very important, as you'll see, gravitational field can be detected in a freely falling reference frame. This is one of these classic thought experiments of Einstein. Einstein's elevator. No external static homogeneous gravitational field can be detected in a freely falling elevator. We're going to prove that now within Newtonian physics. Note that I'm stressing static homogeneous. So if the gravitational field varies, is not homogeneous, is not translation invariant, then you can detect it by tidal forces. It's very important. So let's, how are we going to quantify, how are we going to prove this statement within Newtonian physics? Well, we're going to suppose we have some physical system, right? And we're going to have n non-relativistic particles. And they're moving in a pair force field. Described by big F, which depends on the separations between these particles. And they're not only moving in that pair force field, they're also moving in an external gravitational field. G of x is a constant G, homogeneous static, doesn't change with time. So what do? Well, we apply Newton's second law to get the equations of motion. How do they look? Well, the mass of the jth particle times by its acceleration is equal to the mass of the jth particle times by g, that's the static homogeneous gravitational field, plus the sum of all the pair forces. Right, that's Newton's second law. K runs from 1 to n, and we just assume that f of 0 is 0, just to make this thing work out nicely. So there you go, look at Newton's second law, right? I can certainly see the gravitational term right there. It's the first thing on the right-hand side. But we're not in a freely falling reference frame. So if we make a Galilean transformation, a non-Galilean, right? We're going to an accelerating or freely falling reference frame with respect to this inertial reference frame where things were formulated. What happens? Well, we have to describe that change of variables, and how we're going to do it? Well, we're going to describe it this way today. X prime, the coordinates in the new reference frame are the coordinates in the old reference frame minus a half gt squared, right? We're just going to accelerate freely falling in the reference frame, and t prime equals t. We're not going to, there's not relativity yet, this is Newtonian physics. Then what happens to the equations of motion according to Newton in our new accelerating frame? Well, if you do the change of variable, I mean, it's a little teeny weeny exercise. Literally substituting in for x prime here and t prime already leads you to the answer. Then we see that the equations of motion in this freely falling reference frame are exactly those of Newton. And we cannot detect that we're in a gravitational field. So that's the first demonstration within Newton's theory of UFF and EEP. Now we're going to tell pretty much the same story, but in special relativity. A bit more demanding calculation, and really a good warm-up for you, and a reminder and a check on your special relativity knowledge, which is essential for this course. So we're going to do essentially the same transformation. We're going to consider a particle moving under the influence of gravitational force field and in a freely falling coordinate system, and then we're going to transform to a non freely falling coordinate system and see what the equations of motion look like. These calculations are just meant to give you some facility with non-Galilean, non-Lorentzian type changes of coordinates. But along the way, we're going to see how the features, how many of the symbols in differential geometry will already start to appear, just in these simple calculations here. So according to EEP, there exists for any particle moving purely under gravity or purely under the influence of a gravitational field, there exists for any such freely falling test particle, there exists a coordinate system according to EEP where you cannot detect the gravitational field at that point. You can detect it by tidal forces, but it's a little bit different. So there exists a freely falling coordinate system, and I'm going to write psi 0 through 3 to describe the coordinates in the system, such that, right, there's no force acting on this particle. Now remember here, we're doing now special relativity. This is relativistic dynamics and kinematics that we're talking about now. And I have to highlight to remind you of some of the modifications you have to make to Newtonian mechanics to do relativistic mechanics. So where we've got some new symbols here, where tau is a new symbol. This is the proper time, right? Okay, go and revise the proper time. You've seen it before in just about any special relativity course. And how do you define the proper time? Well, it's defined by the infinitesimal difference minus eta alpha beta d psi alpha d psi beta, or maybe it's a bit easier to see it this way. It's defined by requiring that minus 1 is equal to eta alpha beta d psi alpha d tau, d psi beta d tau. It's the how a clock ticks that moves with the particle instantaneously. And now I've introduced some new notation, right, and some new operations. So we're going to have to explain these things. So this is the new notations that we're encountering. So firstly, we've got this eta. What on earth is eta? Eta is a matrix. It's a special relativity metric. It's a diagonal matrix, which is mostly positive in our course. We'll take the mostly positive convention following Wold. And, well, you know, I told you about components, didn't I? Well, the alpha beta component is also written like this, which is the entry of row alpha and column beta. We're also employing index notation in the Einstein summation convention. So what does that mean? Well, you've seen indices before in the previous lecture, but the summation notation, I mean, you probably haven't been able to avoid seeing it so far, but here it is just to remind you of it. If we've got an expression that looks like this, this means sum alpha 0, 1, 2, 3. So wherever we have a repeated index, so one index is downstairs and one index is upstairs, then we're meant to sum over it. The distinction between downstairs and upstairs we won't make today. Today, if you just see this notation, this is what it means. Later, as we get into differential geometry, I will explain the difference between upstairs, explain what the upstairs and downstairs notation is meant to represent. So here we've just introduced a notation. This should be already familiar to you from your special relativity course. And using that notation, we've talked about or introduced the notion of proper time. So proper time is, tau is defined by this equation here. So you get your coordinates and you differentiate them with respect to a temporal parameter, and you find that temporal parameter or that parameterization of time such that that equation is fulfilled with -1 is equal to this length of these 4 vectors here. All right. Now that's all in the freely with respect to the freely falling reference frame. Right? That's relativistic mechanics in freely falling reference frame. There's no forces m. There's no force acting on our test particle, according to EEP, when we're in a freely falling reference frame. Well, let's suppose now we're going to take a look at things in another reference frame. In fact, we're going to be pretty much as general as possible. We're going to suppose we're going to move to just another coordinate system. It doesn't have to be it doesn't have to be freely falling. It might be static with respect to freely falling observer. It might be in constant motion with respect to freely falling. It might be rotating, whatever. This is a total general calculation. It might be a lab reference frame, rotating, ... So that's, I'm going to just sort of draw a schematic now of these coordinates. So here, these black grid here is meant to represent our new coordinate system. X1 goes along this axis here. X0, which is some of the temporal coordinate, goes up there. And there's an X2 and an X3. And then with respect to these new coordinates, the old coordinates, well, they all look distorted, don't they, right? Maybe we're rotating, who knows, right? Here's the old coordinates here. So this axis here might be psi0 in the old coordinates, and this one along here might be psi1. So we have two coordinate systems, one describing one reference frame, one describing the other. And how do we change coordinates? Well, they're just functions of the other, right? So psi alpha, you can express psi alpha, the freely falling reference frame coordinates, in terms of these non-freely falling reference frame coordinates. As long as you didn't do anything singular, this is you can calculate these coordinates. So at the moment I've got these upstairs indices. Don't worry about that yet. Just follow the notation and the meaning will be explained later. You could have equally well written all these indices downstairs if you want. At the moment there's no difference in their meaning implied. So the force-free equation of motion, the expression of in relativistic mechanics that no force acts. What does that look like? Well, remember the force-free equation of motion says no force, zero, no force acts on d squared psi alpha d tau squared, right? Proper times up there. So let's go check I didn't write nonsense down here. Is that the same as before? Yep. So, but that's in the freely falling reference frame. What does it look like in our crazy reference frame? Well, we've got to substitute. And what does second derivative mean? It means do the derivative twice. So we're going to do it twice. But remember, we've got to do everything with respect to our new coordinate system. So we have to take this total derivative with respect to proper time and express it with respect to the coordinate system coordinates x mu. Right, there we go. All I've done is taken this total derivative and written it in terms of all the partials with respect to the independent variables. And now, well, that's just one total derivative. We need to get rid of the other one in the same fashion. And if you do this, you find the following equation for the force-free equation of motion. So if you apply the second derivative, write the total derivative with respect to all the independent variables as partial derivatives, then you end up with this equation here. And this is an equation that we will see a lot more in coming lectures. It's called the geodesic equation. But here we're just doing things totally at a completely elementary level within relativistic mechanics. So already this is an interesting equation. It's not completely the geodesic equation, right? You know, we've got a term here, and we don't like that. We want to express things in a term which makes, in a way which makes the acceleration terms easier to look at. And so we want to get rid of this yellow term. We can do that. So 0 equals this complicated equation. We can exploit the following, identity, namely that the Jacobian is invertible. D lambda mu is just the Dirac delta, Kronecker delta function, forget Dirac, the Kronecker delta function. So it's 1 if lambda equals mu, or 0 otherwise. So this is just, this is the Jacobian matrix is invertible, that's what that says. So then if we can exploit that, we can multiply both sides. We can multiply both sides by dx lambda d psi alpha to eliminate this yellow term there. And sum, right? And sum. And then that equation up here now takes on the more familiar geodesic equation type form. And I've already introduced some notation that we'll see later when we start doing differential geometry properly. So this is what the equation of motion looks like in our new reference frame. Our crazy rotating, jumping up and down on the trampoline reference frame. This is what the freely falling trajectory looks like. And we've introduced some notation gamma for the so-called affine connection and this is, well, it's okay, I've missed one line, so it's an exercise for you to fill in that line. And this affine connection expresses how the new coordinate, the freely falling coordinates depend on the new coordinate system, and there's also a Jacobian factor in there. And we can also, okay, so let's pause for a moment to just look at this equation here. We're going to see this equation much more generality when we come to formulating differential geometry mathematically. And this equation will be known as the geodesic equation, and it expresses that in a freely falling reference frame, there are no forces acting on a particle. Okay. EEP. It's convenient, when we're in the new reference frame, it's a bit convenient to not have to define the proper time with respect to the old reference frame coordinates. So what we do is we also work out how to calculate the proper time with respect to the new coordinates. That way we're not stuck to going to the freely falling reference frame every time we want to compute something. D tau squared, what is it equal to? By per definition, it's equal to eta alpha beta d psi alpha d psi beta. Well, let's just change our coordinates now, right? We know how to change coordinates. We just change our total derivatives with respect to xi's to partial derivatives with respect to x's. we do some multivariable calculus to do the increment in terms of x's instead of xi's. There we go, that's how we change from having our increment d psi to dx. We pick up these change of variable formulas, and we can define that way a new expression. We could just define something called G. G is a matrix, and that G collects together all the stuff that turned out to appeared when we changed to the new coordinate system. So it's just the blue stuff. So the definition of G is as d psi alpha, dx mu, d psi beta, dx nu is the, and we give a name to it, right? We call it the metric. So these are just, these are calculations you can do within Newton's mechanics, Newtonian mechanics, or relativistic mechanics, where we explore consequences of EEP and UFF and so on. This doesn't completely get us to general relativity. Here we're only seeing one aspect of general relativity, a very important aspect, namely that the geometry of space-time tells freely falling particles how to move. The geometry of space-time will be later captured in this course by the metric G mu nu. G mu nu will be all that you need to describe the geometry of space-time. And with that, you'll be able to derive the trajectories of freely falling particles. But that's only half the story, right? General relativity is an amazing theory because it combines a back action of matter on the gravitational field. And that's comes as a consequence not just of EEP, also of something called Mach's principle. This is the second underlying the second key idea underlying GR. And it's a bit more diffuse. It's a bit harder to make precise, but it was highly influential to Einstein. And so in second key idea, well, really we should replace the word idea with circle of ideas, set of ideas. It's less precise. You can't formulate it so nicely. But very, very influential. I'll give a summary of these ideas in the following statement. It's a modern interpretation of what Ernst Mach was on about. And the summary is something like this. All matter in the universe should contribute to the local definition of non-accelerating and non-rotating. Conversely, in a universe devoid of matter, there should be no meaning to these concepts. And this is really pretty deep, right? You know, these concepts don't make sense without matter. You need matter to give sense to the notion of non-acceleration and non-rotating. Now, Einstein took these ideas and these observations and these calculations and similar calculations to these, and over a long period of time conceived of and carried out the formulation of the theory that we now know today as general relativity. I'm going to give you a short description of general relativity as formulated by Einstein. It's possible to state what the theory is, even at this quite descriptive level, but getting at the quantitative consequences of these statements takes a lot more work. But nonetheless, you can still appreciate Einstein's theory with little more than what I've shown you in these first two lectures. So the first part of general relativity is the statement that the observer-independent properties of spacetime are described by a spacetime metric, which is a matrix of 4 numbers at every spacetime location, which need not have the flat form of special relativity. Okay. Now comes the bite. Curvature is that property of the metric that accounts for the physical effects of gravitation. So that's the first part, or the second part of the formulation of general relativity. Curvature is a property of the metric, so you can first statement is that spacetime is described by a spacetime metric. Second part is that the property of this metric field that accounts for the physical effects of gravitation is curvature, which I'll come to defining in the coming, say, 3 or 4 weeks. And further, and in a sense, you could discover already the statement that curvature is accounting for the physical effects of gravitation. That's from calculations we've done today. But the part that we haven't really discussed today, and we will discuss later, is that curvature is determined itself by matter. Well, not really just matter, actually. Matter is perhaps oversimplifying it. Curvature is determined by the distribution of stress energy and momentum in space-time, and therefore, and then vice versa. So there's this continuous interplay between the distribution of stress energy, which affects the curvature of space-time. Curvature affects the locations of test particles, or test masses, and test masses are masses, right? A part is matter itself. Curvature tells matter how to move on these freely falling geodesics, which then redefines what it means for the distribution of stress energy, redefines the distribution of stress energy, which changes the curvature and so on. And so this So stress energy tells space-time how to move, and curvature tells how matter moves. So there's this non-linear, it'll turn out to be non-linear interplay between these two concepts. They determine each other. And the extraordinary thing, the almost divine aspect of general relativity is that this holds together. It doesn't blow to pieces and become inconsistent. This leads to a beautifully consistent theory, a complete theory of essentially of itself. And that's an amazing thing that such a thing could exist, especially when you work at trying to build these kinds of theories and you find that it's not so trivial to come up with something like that that all holds together. Well, that's a story for another, let's say, 20 lectures. So the plan is, this is your first 2 lectures of general relativity. You've seen the key principles underlying the formulation of general relativity. You've seen Einstein's equivalence principle, you've seen Mach's principle, we've done some calculations in moving between reference frames, but actually implementing and carrying out the physical content of Einstein's formulation of general relativity, it's not sufficient really with the maths that we have currently at our disposal. We have to develop the mathematics of curvature, the mathematics of space-time manifolds that aren't flat. And that requires a bit of work. Without work, you can't expect any payoff. You only get what you put into it in this course, and that's the work that we're going to commence next week in lecture 3. But for now, that's it. Thank you very much. Goodbye.